That familiar silent face in our night sky has been hiding a few secrets, you know. For millennia, humanity has gazed upon the moon, weaving its steady presence into our myths, our calendars, and our dreams of exploration. We thought we knew it as a simple barren rock, a quiet companion on our journey through the cosmos. But the story of what lies beneath its dusty, cratered surface is far more dynamic and complex than we ever imagined. We are now finally beginning to piece together the moon's inner autobiography, and this new chapter reveals a world forged in fire, with a surprisingly active interior and resources that could shape our future. The moon is not just a dead world, it's a geological time capsule waiting to be read. This fresh understanding doesn't come from idle speculation but from decades of patient scientific inquiry. From the seismic tremors recorded by Apollo astronauts to the precise gravitational mapping by modern orbiters, we have developed a new kind of vision. This vision allows us to peer through hundreds of kilometers of rock to sketch out the moon's internal anatomy. Our journey begins at the surface with the moon's outermost layer, the crust. This is the part of the moon we see, a shell of rock that bears the scars of more than 4 billion years of cosmic history. It is not a uniform blanket but a landscape of dramatic contrasts. The bright, heavily cratered areas we call the lunar highlands are composed of a lighter type of rock known as anorthosite. These are the oldest parts of the crust, the primordial shell that solidified from a vast ancient ocean of magma that once enveloped the entire moon. Think of them as the moon's original battered armor, a testament to its chaotic youth. In stark contrast are the dark, smooth plains known as the Maria or seas. These are not bodies of water but vast basins filled with solidified basaltic lava. These dark patches are younger than the highlands, formed when intense heat from the moon's interior caused molten rock to well up and flood massive impact craters. This volcanic activity, which peaked billions of years ago, resurfaced large portions of the moon, creating the iconic man-in-the-moon patterns we recognize from Earth. The distribution of these Maria is curiously lopsided. One of the most profound discoveries about the crust is its variation in thickness. Data gathered by orbiting spacecraft, such as NASA's Grail mission, revealed that the crust is significantly thicker on the far side of the moon. On the near side, it averages about 30 to 40 kilometers deep, while on the far side, it can be up to 60 kilometers thick or more. This asymmetry is a major geological puzzle that likely holds a key to understanding the moon's earliest environmental conditions and its relationship with a young, hot Earth. The thick far-side crust may have simply been too robust for magma to easily punch through. Beneath the visible surface lies a layer of broken rock dust debris called the regolith. This powdery blanket, which can be several meters deep, is the product of relentless bombardment by micrometeorites over eons. It is within this fine-grained material that we have found some of the first hints of water on the moon, as particles from the solar wind implant hydrogen atoms that can then bond with oxygen in the soil. The crust, therefore, is not just a static shell, but a dynamic boundary, recording the history of both internal volcanism and external impacts, while also acting as a repository for resources from space. What we've found is a layered world, much like our own Earth, but with its own unique history and characteristics. Beneath the crust lies the moon's thickest layer, the mantle. This vast region of dense, silicate rock makes up the bulk of the moon's volume and mass. While it is solid today, the mantle was once a much more turbulent place. Billions of years ago, it was partially molten, a churning engine of heat that drove volcanic activity, responsible for creating the dark Maria on the surface. The chemical composition of the Apollo moon rocks, which are largely derived from this mantle material, gives us a direct sample of what this layer is made of, primarily minerals like olivine pyroxene, similar to Earth's own mantle. Our most intimate knowledge of the mantle's structure comes from listening to the moon's faint heartbeat. Moonquakes. The seismometers placed on the surface by the Apollo astronauts operated for years, recording thousands of these subtle tremors. By analyzing how the seismic waves from these quakes travel through the moon, scientists can deduce the properties of the material they pass through. Just as light bends when it enters water, seismic waves change speed and direction as they encounter layers of different density and temperature. This seismic data has been crucial for confirming the existence of the mantle as a distinct layer. These moonquakes originate from different sources. Some are shallow, caused by the impacts of meteoroids. Others are triggered by the gravitational pull of the Earth, which rhythmically squeezes and stretches the moon. But the most revealing are the deep moonquakes which occur hundreds of kilometers down, near the boundary between the mantle and the core. The patterns of these deep quakes suggest that the lower part of the mantle is not entirely solid. There appears to be a partially molten zone at the very bottom of the mantle, a warm and somewhat soft layer that slows down seismic waves passing through it. This partially molten layer is a critical piece of the puzzle. It helps explain how the moon, despite being much smaller than Earth and cooling off faster, was able to sustain volcanism for hundreds of millions of years. This warm, deep layer could have served as the source for the magma that flooded the surface basins long ago. It tells us that the moon's interior is not a completely cold, inert block of rock. Even today, there is a residual warmth deep inside, a faint echo of the fiery processes that shaped its past and continue to cause a gentle stir in its deep interior. As we assemble this new portrait of our lunar neighbor, we are reminded, things are rarely as simple as they appear. The serene, white glow of the full moon belies a history of immense heat, planetary collisions, and ongoing geological murmurs. The quiet stillness of its surface conceals a treasure trove of information about the early days of our solar system. This essay will take you on a journey deep into the moon, layer by layer, exploring the evidence that has reshaped our knowledge and revealed the dynamic, hidden world that lies just 250,000 miles away. A world we are only now getting to know. At the very center of the moon lies its core, a feature whose existence was debated for decades. Unlike Earth, whose massive iron core dominates its interior and generates a powerful magnetic field, the moon's core is remarkably small. It accounts for only about 1 to 2% of the moon's total mass, making it one of the smallest cores relative to size. But refined analysis of seismic data and precise measurements of the moon's rotation have finally brought this hidden region into focus, revealing its complex structure. Modern science has confirmed that the moon does indeed have a metallic core likely composed mostly of iron, sulfur, nickel. More surprisingly, this core is not a single solid ball. Instead, it seems to have a structure similar to Earth's, with a solid inner core surrounded by a fluid outer core. The solid inner core is estimated to be about 500 kilometers in diameter, while the molten outer core extends out to a radius of about 330 kilometers. This structure was inferred by studying how the moon's spin wobbles slightly as it is tugged by Earth's gravity, a motion influenced by the state of its deepest interior. A churning, molten iron core can act as a dynamo, generating a magnetic field. While the moon today has virtually no global magnetic field to speak of, some of the oldest moon rocks brought back by the Apollo missions show evidence of being formed in the presence of a strong magnetic field. This suggests that billions of years ago, the moon's core was churning much more vigorously, creating a magnetic shield that has long since vanished. The tiny, partially molten core we see today is the last remnant of that ancient active dynamo. This discovery helps solve a long-standing mystery about the moon's past, but it also deepens our appreciation for its unique evolution. The small size of the core is a major clue that supports the leading theory of the moon's formation. If the moon was formed from debris blasted off Earth's outer layers during a giant impact, it would make sense that it ended up with a disproportionately small amount of the dense iron that had already sunk to Earth's center. The moon's tiny core is therefore not just a geological feature, it is a piece of evidence that tells a story of cosmic collision and shared origins with our own home world. Our picture of the moon's hidden interior is not guesswork. It is a mosaic built from multiple lines of evidence collected over more than half a century of exploration. The first and perhaps most important tool has been seismology. Between 1969 and 1972, Apollo astronauts deployed 4 seismic stations on the lunar surface. These incredibly sensitive instruments listened for moonquakes for nearly 8 years, recording the faint vibrations traveling through the moon's body. By timing the arrival of these seismic waves at different stations, scientists could begin to map the boundaries between the crust, the mantle, the core, much like a doctor uses an ultrasound to see inside a patient. Another powerful technique involves mapping the moon's gravity field with extraordinary precision. Missions like NASA's Grail, which consisted of 2 spacecraft flying in tight formation, measured minute variations in the distance between them as they orbited the moon. These tiny changes were caused by differences in gravitational pull from the surface below, indicating areas of higher or lower density. This data allowed scientists to create a high-resolution map of the moon's internal structure, revealing the variable thickness of the crust and confirming the presence of dense, solidified magma intrusions beneath the Maria. Of course, nothing beats having a piece of the object in your hands. The 382 kilograms, 842 pounds of moon rocks and soil returned by the Apollo missions are an invaluable source of direct information. By analyzing the chemistry-mineralogy age of these samples, we can anchor our remote sensing data to physical reality. These rocks tell us what the crust parts of the upper mantle are made of. They contain trapped gases that reveal the history of the solar wind, and their magnetic properties hold the ghost of the moon's ancient magnetic field, providing tangible proof of a once active core. Finally, advanced remote sensing from lunar orbiters like the Lunar Reconnaissance Orbiter has provided a wealth of complementary data. Laser altimeters have mapped the moon's topography with incredible detail, while spectrometers have analyzed the composition of the surface from afar, identifying minerals and searching for the signature of water. When combined, these different methods, seismology, gravity mapping, sample analysis, remote sensing, cross-check and reinforce one another, allowing us to build a confident and increasingly detailed model of a world that we cannot directly drill into. So, how did the moon come to be? With its layered interior and peculiar chemistry, the leading scientific explanation is the giant impact hypothesis. About 4.5 billion years ago in a chaotic early solar system, a Mars-sized protoplanet named Theia collided with the young Earth. The impact was a glancing blow. It vaporized the impactor. It blasted Earth's crust into orbit. It blasted Earth's mantle into orbit. The orbiting cloud of superheated rock and vapor coalesced. Gradually, it clumped together to form the moon. This catastrophic birth explains many puzzling features. It explains why the moon is so large relative to Earth, and why the moon's orbit is tilted. The intense heat drove off volatile elements. For example, water boiled away. That's why lunar rocks are much drier than Earth's. The moon was essentially baked dry at its creation. The theory also explains the moon's small iron core. Earth had already differentiated. Heavier elements like iron had sunk, forming a large central core on Earth. The impact scraped off material from Earth's outer layers, the mantle, the crust. Those layers are poor in iron, so the debris forming the moon lacked dense metals. Result, a disproportionately small lunar core. The moon is largely made of the same stuff as Earth's mantle. Recent refinements use precise isotopic analysis of Apollo moon rocks. Those analyses show Earth and the moon have nearly identical isotopic signatures for elements like oxygen. It's like a geological DNA test. That implies material from Earth and from Theia was thoroughly mixed in the debris cloud. Some newer models propose a far more energetic impact. That would have completely vaporized Theia, and vaporized a large portion of Earth, creating a massive donut-shaped cloud, a synestia. From that synestia the moon later condensed. For decades, the moon was considered the driest place in the solar system, a completely desiccated world. The Apollo samples seem to confirm this, containing almost no water. This picture began to change dramatically in the 21st century with a series of groundbreaking discoveries. In 2009, NASA's L-Cross mission intentionally crashed a probe into a permanently shadowed crater near the moon's south pole. The resulting plume of ejected material was analyzed and found to contain a significant amount of water ice, a stunning confirmation of a long-held theory that these frigid traps could hold frozen volatiles. This discovery opened the floodgates. Subsequent missions, including India's Chandrayaan-1 and NASA's LRO, used instruments that could detect the chemical signature of water from orbit. They found evidence of water not just at the poles, but spread thinly across the entire lunar surface, bound to grains in the soil. The amounts are minuscule, far drier than the driest desert on Earth, but the fact that it exists at all was a revelation. It is thought that this surface water is created by the solar wind as hydrogen ions from the sun bombard the lunar soil and combine with oxygen present in the minerals. Beyond the icy poles and the surface soil, scientists have even found water trapped inside the moon's rocks. By re-examining the iconic green glass beads and orange glass beads brought back by the Apollo astronauts, tiny droplets of volcanic glass formed during fire fountain eruptions billions of years ago. Scientists using modern techniques discovered water molecules locked within them. This was a bombshell. It meant that parts of the moon's deep mantle, the source of this ancient magma, must have contained water, challenging the idea that the moon was born completely dry. The presence of water on the moon is more than just a scientific curiosity. It's a game-changer for the future of human exploration. Water is a critical resource. It can be used for drinking, for growing plants, and, most importantly, it can be split into hydrogen and oxygen. These two elements are the primary components of rocket fuel. The ability to, live off the land and manufacture propellant on the moon could transform it into a crucial logistical hub, a gateway to the rest of the solar system. The moon's hidden water may very well be the key to our future in space. The moon is tidally locked with Earth, meaning it rotates on its axis at the same rate it revolves around us. The result is that we only ever see one face, the near side. The far side remained a complete mystery until the Soviet Luna 3 probe photographed it in 1959. What it revealed was a world strikingly different from the one we knew. The familiar dark seas or Maria that create the man in the moon on the near side are almost entirely absent on the far side. This stark difference, known as the lunar dichotomy, is one of the most significant unsolved puzzles in lunar science. Why would one hemisphere be so different from the other? The leading hypothesis connects back to the moon's formation and its relationship with a young, hot Earth. Shortly after its formation, the moon was much closer to Earth than it is today. The near side would have been baked by the intense radiant heat from the still glowing molten Earth, while the far side, facing away into cold space, would have cooled much more rapidly. This temperature difference could have had profound geological consequences. Volatile elements and minerals would have vaporized on the hot near side, migrated to the cooler far side and condensed, contributing to the formation of a thicker crust. That thicker crust acted as a barrier, making it much more difficult for magma to erupt, while the thinner, near-side crust provided easier pathways for lava to flood basins. The far side's rugged face is essentially a relic of this ancient thermal gradient. China's Chang'e 4 mission began the first on-site exploration of this enigmatic terrain, helping test these ideas. After centuries of observation and decades of intensive exploration, the moon has transformed in our understanding from a simple, static satellite into a complex and dynamic world in its own right. We now know it has a layered interior with a warm lower mantle and a small partially molten core. We have confirmed the presence of water, a resource with profound implications for future exploration, and we have pieced together a dramatic origin story that links its fate with our own. The moon is Earth's cosmic sibling, a geological museum, and a launch pad to the future. Each new discovery, from the faintest moonquake to the tiniest drop of water, deepens our connection to our place in the universe. We look up at the same moon our ancestors did, but now we see a neighbor with a story to tell, and a future to share.